Hello, today's video is going to introduce you to exponential and logarithmic functions. Specifically, we're going to start with solving exponential equations using common bases. So our steps are listed here, but they don't make a lot of sense until we actually dive into an example. So let's look at number 1. Our instructions or our steps say to use the properties of exponents to simplify each side of the equation. Well, this is already simplified, 2 to the x plus 1 power. There's nothing really to do there. And 2 to the 9th, even though, yes, we could actually calculate 2 to the 9th, we don't want to do that because if you look at the next step, it says to rewrite the equation so both sides have the same base. Well, both sides already have the same base. So then step 3 tells us to drop the bases and set the exponents equal to each other. So what I want you to think about is that if 2 to this power equals 2 to this power, then shouldn't the powers equal each other? And so those exponents, we are going to just forget about the bases because the bases are the same. And these exponents have to equal each other. So if we know that x plus 1 equals 9, then x must equal 8. And that's it. That is the solution to this exponential equation. So let's look at number 3 because it's a little bit different. The first thing that we want to do is we want to combine these two terms. We want to simplify the left side of the equation. And when we multiply with exponents, if they have a like basis, you multiply, let me use my words correctly. When you multiply like bases with exponents, you add the exponents. So we keep the base the same, so the 3's don't change, but then we have k plus 2 equals 3 to the 5k minus 1. And now, you could have written this as 2k plus 2, that's fine. We're going to do that in the next step anyway. Okay, so now we have like bases, and we have the same thing equal to each other. So we can just set those exponents equal to each other. So I'm going to simplify it now to 2k plus 2 has to equal 5k minus 1. And whenever we solve that, we are going to get k is equal to 1. Now, what about when we have equations that do not have a common base? That is our next question. If we go back to what our instructions said, it said to simplify and then rewrite the equations so that both sides have the same base. Well, if we look here, we have a base of 6. Is there any way that we can have a base of 6 and give it an exponent to make it equal 36? Yes. 6 squared is equal to 36. So we can rewrite this as 6 to the 2x minus 10 equals 6 squared. And now we have like bases, and we can just set the two exponents equal to each other. And we are going to find that x equals 6. All right, number 7 is a little bit different. These each have like a unique trait to them. So that's why I chose these. All right, number 7, if we look at the two bases, so we're looking at 7 and 1/7. We want to think about how can we write these with a common base. So they both have a 7 in common, so let's just see if we can do something with that. So this is already 7 as a base. And the right side, what power could we raise 7 to get 1/7? And the answer is -1. Because remember that the rule is m to the negative I'm trying to remember how to write this. A to the negative m power equals 1 over a to the m power. Or a over b to the negative m power equals b over a to the negative m power. So it just flips out to the positive. I did that wrong. Shoo! So a negative exponent flips the fraction. So remember that whole numbers are over 1, so we're just flipping the fraction. It makes it a reciprocal. All right, now that we had our little review lesson, back over to number 7. We now have common bases, so we're going to have 4x plus 11 equals negative 1. And we are going to find, when we solve that x is equal to negative 3. So let's talk about number 9. All right, on number 9, we want to look at our bases, 27 and 3. And we want to think about how we could try to come up with a base in common. Well, 3 is a prime number, which makes me think that it's not really going to be able to be broken down anymore. And 27 is a perfect cube. And this is something that you might have to like mess around with guessing and calculating to figure out. But how could we raise 3 to a power to make it equal 27? We could cube this, 3 to the third power. So 3 to the third power equals 27, and then we've also got this exponent out here. So this is what we have now. Well, whenever we raise a power to a power, we multiply the powers together, the exponents together. So this is a binomial, so we'll have to distribute that 3. But this is going to equal 3 to the 6x plus 18 power equals 3 to the 2x. So now we have common bases, and we can set the exponents equal to each other. And we will find that x is equal to negative 9/2. And the last problem I'm going to do with you is number 11. And with number 11, we want to try to decide what base we can use. So your first instinct might be to use 25 as a base because it's the smaller number. And typically, the way we've been doing this, the smaller number is the base. But 25 squared is a big number. And 25 squared is 625. It's not 125. And the square root of 125 is not an even square. So we need to find some other root in common. Well, 25, you can ask yourself, does it have a square root? Does it have a cube root? Does it have a fourth root, etc.? But it has a square root. So when we ask ourselves that question, does 25 have a square root? The answer is yes, and 25 is equal to 5 squared. So let's see if we can come up with 5 to some power and make that equal 125. And if you do some testing, some trial and error on your calculator, you should find that 5 cubed is equal to 125. So we should have 5 cubed to the y power. Then we will simplify this. And now we can see that 3y has to equal 2. And that means y is going to equal 2/3. So that is all the examples I'm going to do with you. Go ahead and finish the rest of this worksheet and make sure you let me know if you have any questions. Have a great day.